Hi everyone, this is going to be a walkthrough video for questions 7D and 7E on Fall 2020 CS621B Midterm 1. Okay, so let's start off with question D, or question 7D, move to front. Suppose that the int linked list deck implements the FA20 midterm list interface given below. Okay, so we have some interface which has a bunch of functions. Perfect. Suppose we want to add a default method move to front with the signature below. Okay, so a quick refresher on what default functions are. If an interface has a default function, all classes that implement that interface have access to that default implementation. Okay, so it's pretty cool. Okay, this method should move all instances of x to the front of the list. For example, if we have the list below, we call move to front on 10, all the 10s move to the front of the list. Okay, as we can see, the items have all been moved to the front. You may assume all of the methods in FA20 midterm list, the interface have been implemented properly, okay? And we can use a maximum of 10 lines. Okay, so looking at this problem, we can kind of break it up into two steps that we probably want to execute. We first want to remove the 10s, and then we want to add them back in the beginning, okay? So how can we remove the 10s? Let's see what functions we have. We have remove first, remove last. Well, they might not be in the front and the end. We also have this remove one, right? This is what we implemented in the previous part, so it's probably going to be used, okay? So this function is going to take in an int x, and it's going to return true if we've deleted that int x, and returns false otherwise, okay? So let's look at a quick example. Let's say that we have these numbers, 1, 2, 10, 10, 4, 10, 7, 10, and we call remove 1 on 10, right? So what'll happen here is we will remove this 10 and we will return true, okay? So this returns true, okay? Now let's say what happens if we call remove 1 on 10 again. Okay, we'll remove this 10 and the function will return true. Let's call it again, right? We remove this, we call it again, and we remove this 10. So as you guys can see, we should keep calling remove 1 on 10 until remove 1 on 10 returns false. Because the next time we call remove 1 on 10, it's going to return false because there's no more 10s to remove. Perfect. Okay, so the idea here is we keep calling move 1 on 10, or x to be more generalized, until it gives us false, okay? Because that tells us that we removed all instances of 10. Okay, so how can we kind of implement that in code? Well, let's see. Okay, let's get to these drawings. So we'll have some while loop, and the condition for our while loop can be remove 1 on x. Okay, what happens here is while this is going to give us true, we'll keep removing instances of x, right? Until it becomes false, upon which we terminate from the while loop. So what should we be doing in the while loop? Well, we probably should be counting the total number of x's we remove so we can reinsert them in the beginning. Okay, so we'll create some int count, and then say count plus equals 1, right? Because we need to keep track of every time remove 1 of x gives us true, we should increment the count. Okay, so after executing these lines of code, we know that in the current state of our list, there's no more instances of x. All we need to do is re-add all of the x's we removed to the beginning of the list. Okay, so what we can say is for int I is equal to 0, I is less than count I plus plus. We will say, well, what can we say? We have access to these functions. We want to add first on x, right? So here's the solution. But if you guys noticed, there is a shorter, more clever solution. Well, what is that? I'm sure you guys are curious, and I am also curious. So let's try to figure that one out. Okay? So this is the iterative solution, and the shorter, more clever solution sounds like recursion. Okay? Let's play with some example. See how we can use recursion here. Okay, my screen's kind of lagging. Okay, let's say that we have a smaller list, 1, 2, 10, and let's say 2 10s, okay? And we call move to front on 10, okay? And this is the current state of the list. So if we were to use recursion, we'd probably have to do some sort of recursive call. The recursive call we'd do would be move to front on 10, right? No other recursive call would make any sense. So if we were to call this recursively, it would go forever unless we removed a 10 before we did the recursive call, okay? So my idea, which I will now translate into code, is we will try removing one instance of x. If this returns true, that means that we removed one instance of x, and we will call move to front on x, okay? Now, what's going to happen is after executing these recursive calls, we will have this will be the first call to move to front on 10, where this is the state of our list. Then we call move to front on 10 again, where this is the state of our list. Then we have one more call to move to front, right, on 10, where the current state of the list is 1, 2, and there are no 10s, okay? So what's going to happen in this case is as we go back up the recursive calls, all we have to do is add 10 back to the beginning of the list, okay? So looking at this example, what we want to do is this base case, we just don't do anything. Then once we get back up to this case, we'll say we removed this 10, so we'll add it back here. Then when we get back to this case, we'll add the 10 that we removed back to the beginning, okay? So if this didn't make sense, let's try to look at the code. I think it'll clear things up. If we successfully remove an instance of x, we'll do the recursive call. Then, as we go back up these recursive calls, we will keep adding x to the front, right? We'll keep calling add first on x, okay? And a quick way to prove this works to yourself is what's going to happen is we have this recursive stack of calls. As we move down this recursive stack, right, as more recursive calls are executed, we keep removing 10s until we get to the bottom and there are no more 10s in the list. Then as we go back up, we keep plopping all of the 10s we removed back to the front, right? So this is the slicker recursive solution, and not many students came up with this, so it's very hard. So don't think about I have to do this in the future. This is just a cool alternate solution. Okay, so exciting. Let's move on to the next question. Public int ripple remove another default function. Exciting. This method has strange behavior. Hey, it's an exam. It attempts to remove all instances of x. If it deletes at least one copy of x, then we'll also delete all copies of x minus 1. If it deletes at least one x minus 1 from the list, it'll delete x minus 2, and so forth, until it can find no more numbers to delete. For example, if we have the FA20 midterm list containing these values, and we call ripple remove on 10, the list will contain these values, okay? So I'll explain what's happening. What we're going to do is if we call ripple remove on 10, we try to delete at least one copy of x, okay? It'll try to remove all instances of x. Sorry, I take that back. So we delete a 10 and we delete this 10. Then it'll say, if we deleted at least one 10, which we did, we will try to delete all copies of 9 or x minus 1. Right? Then we delete 2 9s, and then it tries to delete all copies of x minus 2, or 8. So it deletes 2 copies of 8. And then since we deleted an 8, we will try to delete all copies of 7, but there are no copies of 7, so we stop. Okay? So the gist of what this function is doing, just to reiterate, is we try to delete all instances of x. If we get to delete at least one instance of x, we try to delete all instances of x minus 1. If we get to delete at least one instance of x minus 1, we try to delete all instances of x minus 2, and this pattern continues, okay? So looking at this code, we also need to keep track of the total number of items we deleted, because that is the return type of ripple remove, right? It says right here, ripple remove should return 6, since it deleted 6 items in this example, okay? Now, we have this code here, and we have an intimidating 4-line solution, but we're first going to start off with a slightly longer, more intuitive solution before we get to this one. Okay. And as usual, let's try to think about how we would approach this problem just intuitively. So the first thing I would say is let's try to delete all instances of 10, right? Looking at this list right here, we should first try to delete all the 10s. Then we'll say, hey, did we delete a 10? If we did, then we'll probably try deleting all 9s, and so on. Okay, so how can we delete all instances of 10 from the list? Well, using this previous part, okay, using the old solution in the previous part, we remember we can use some sort of while loop. Okay, so my idea is we will first delete all instances of x. Okay, how we can do that is we'll have some while loop, which will keep going, right, until we remove one of x returns false. And I'm mimicking the same iterative solution I did to the previous problem. So if you guys were confused on if this doesn't make sense, watch like earlier in this video. Okay. And we should also keep track of the total number of items we deleted, because that's what the return type of this question is. So, okay. Now, what we've done is we've successfully deleted all instances of 10. Okay. The next step is to see if we deleted a 10, we should try deleting all instances of 9, and so on. Okay. So if our count is greater than 0, what we should do is try deleting all instances of 9 and repeating the same thing that we're doing right now with 10. Okay, so if we're repeating the same thing we're doing with 9 that we just did with 10, it kind of indicates a recursive call, right? So we should probably do a recursive call to x minus 1, right? This will try to delete all copies of x minus 1, and it'll continue the pattern for us. This will give us a count of the total number of elements that this recursive call deleted, and we should add that to our existing count. Okay, so what we can do is return our count plus ripple remove x minus 1. Okay, now we can say if the count is not greater than 0, if the count is equal to 0, it means that we didn't get to remove anything, in which case we should return 0. Okay, so this is the solution. Let's give one more walkthrough. In this step, what we do is delete all copies of x. Here we ask ourselves, if we got to delete at least one copy of x, well, we should start deleting x minus 1s, which we do in this recursive call, and we accumulate the total count by summing them up together. Okay, if we didn't delete anything, then we return 0. Okay, perfect. So the next thing that we should discuss is this 4-line mysterious solution. So this is very exciting. It may not be intuitive, so don't worry if it doesn't come to you guys, but I'm going to show you guys anyways. Okay, so let's look at this question right here. Let's look at this prompt. We have this list. When we remove a 10, what is our next line of action? Like, what should we do next? We should try removing all of the 10s that are remaining, and we should try removing all of the 9s. Okay, so do you guys kind of see how that might spring two calls? We have to call ripple remove on 10 again, and we also have to call ripple remove on 9. Okay, so what we can do is we can say if remove 1 on x, right? This is saying that we successfully removed a 10 in this example. We still need to delete all of the other 10s, and we need to delete all of the 9s. And right, if the 9 call works, then all of the 8s, and so on. So what we can say is we should probably call ripple remove on x again. We should also call ripple remove on x minus 1, right? And we should probably sum these together to get our answer. And then we also need to add 1 to this to count for the one that we removed. Okay, so return 1 plus ripple remove on x plus ripple remove on x minus 1. Okay, and then in the case that remove 1 returns false, what we should do is return 1, 0, probably 0, because we didn't remove anything. Okay, so just a quick recap of why this solution works. What's going to happen if we're using this example is we'll call ripple remove on 10. Okay, what that's going to do is it'll remove a 10 because of the remove 1 of x. Then it'll return 1 plus ripple remove on x. Okay, so we call ripple remove on 10. What that does is it removes this 10, and then we return another recursive call, 1 plus ripple remove of 10. Okay, so the next recursive call, ripple remove of 10, okay, will give us 0 because there's no more 10s. Okay, so now what we do is in this recursive call, then we call ripple remove on x minus 1. Okay, and this continues this process, right? It'll delete the 9 and have its own sequence. So I encourage you guys play around with this example. I'm going to stop here. And yeah, that is all for this video. Hope you guys enjoyed it and have a good rest of the week.